Ah, kids. All right, you should have already done the intro sheets in your packet, so this is kind of going over it. So let's just kind of go over that. So let's pretend I have an object. I think I have a cart, and my cart is going to fall straight down. Um, in If we were doing this in kinematics, here's what you would do. You would say, well, here's my picture. You would write down your givens. You know this. You know the acceleration is 9.8 meters per second squared down, or maybe negative, depending on which way you're calling negative. You know your initial velocity is 0, or maybe you could solve for your final velocity. Okay. Here's how you would do it with energy, where the system is just the cart. Remember, if the system is just the cart, then the only force acting on it is gravity. Or sorry, the only energy available is kinetic energy, which means, and I was getting ahead of myself. If I was to draw an outside force, the outside force acting on my system, it would be the force of gravity. So if you were to do your picture, so part A is up here, part B is down here, and it's going to go like this. So if I go A to B, well, at A, what type of energy does my system have? It has nothing. At B, what type of energy does it have? It has kinetic. And then going from A to B, is there an outside force? Darn right there is. So then there was some work done, which also makes sense because if my energy is changing, there had to be some work done. And then you would say, well, the work done is the force of gravity times that vertical distance. Over here we called it y, so we'll call it y again, equals kinetic energy, which is 1/2 mv squared. And then do you see how you could solve for v? Okay. I'm going to show you that that's easier than this, but it's still not easy enough, which is why you did this whole thing where you were introduced into potential energy. Okay, so then later on it said, all right, so rather than going straight down, we're going to go down a ramp where that's still the same distance. This is some angle theta, and you have this thing moving down here. I'll call this d, okay, the distance that it's going to move down there. You're supposed to draw an FBD, so if I draw my FBD is going to look something like this. Normal force, and then force of gravity, okay? And first you're supposed to go, I'll label some points, A, B, and then later on you went A to point C, okay? So if, again, we are saying you have the cart only, and I'm going to go from A to B, well, what type of energy do I have at A? Oh yeah, I got nothing. What type of energy do I have at B? Oh yeah, I have kinetic energy. Going from A to B, was there any work, outside forces acting? Well, the normal force is an outside force, okay, because it's not part of the cart. Well, is that going to do work? And the answer is no. The force of gravity is an outside force. Is the force of gravity going to do work? No, but that component, FG parallel, would do work. So there's definitely some work done, and then this is going to be FG parallel times that distance, which we labeled d, equals this, which is equal to 1/2 mv squared. And hopefully you've done this enough now where you know FG parallel is going to be mg sine theta times d equals 1/2 mv squared, and you can cancel out your m's and you can solve for v. Okay. If we were doing it rather than A to B, if we're going to say, hey, I would rather go A to C, but again, we're talking about the cart only. What type of energy do I have at A? Well, I got nothing. What type of energy do I have at C? Well, I have kinetic. Okay. If I decide I'm going to go from A to B and the only force acting is going to be gravity, well, in that case, that's going to be this, which is going to be Fg. So yes, there's work done. And this work done would be Fg. And here's where it's pretty cool. It would really be times this y. But if you look, y equals d sine theta. So use your mad trig powers. So then F times d, which would be d sine theta, because this and this have to point parallel, equals 1/2 mv squared. So I get mg d sine theta equals 1/2 mv squared. My m's go away, and hey, look, I get the same thing. That's pretty fun. Okay? Then I would attest this is still not easy enough. Okay? So then it introduced, well, what happens if the Earth is part of your system? Well, if the Earth is part of your system, I'm incorporating gravity as part of my system. Well, if gravity is part of my system, now I have potential energy due to gravity that's available. Why? Because if you lift something up, if here's the ground and I have something up here, this object now has the potential to do work. It has a new type of energy, which we're calling potential energy due to gravity. Okay? So hopefully that makes sense. That should make sense to you. And if you were to do this now so that your system is the cart plus the Earth, okay, where if it's the cart, I just have kinetic. Well, kinetic plus UG, potential energy. That's what I have available to me. So it doesn't really matter if I go A to B or A to C, so I'll just say I'm going to go A to B because that's really what the cart's doing. Remember, there is no friction. We'll talk later on how we do this if there is friction. But what type of energy do I have here now? Well, now, do I have the potential to fall? I do. So that would be UG. What type of energy do I have there? Oh, that's kinetic. Going here to here, well, that's what my FBD looks like. But remember, this is part of my system, because really this is part of my system. So the only force I have left is Fn. Is that going to do work? No, it's not. So then equals. And then this is equal to mg. Now, here this should make sense to you. Do you see how, look at all my equations here. Do you see how I have mg, and then there's d sine theta, and then I have mg, this d sine theta? Well, what was d sine theta? Oh yeah, it's the height. So it's really mg times y. Does everybody see that? Which should make sense, because if I have ball A here and ball B there, which ball has more potential energy? This one. Why? Because it has more potential to fall. So that's my form of potential energy. But really, look, it's just F times D. Okay? Equals 1/2 mv squared. And then, hey, look, you're going to get the same thing. That's way easier, though. Okay? So that's potential energy. Hopefully that makes sense. Bye, kids.